All right, stat students, it is time for the sampling distributions unit test. Here we go. Okay, so it says a group of science students plan to take a simple random sample of 25 days a year to see. We'll just read silently now. Okay, now really this unit is super important because it leads into getting comfortable with all the formulas you end up using in hypothesis testing. So things to understand is when you read this, this is a proportion. That means also p hat, our sampling distribution, is going to be based on a proportion. Now the proportion we use for our sampling distribution is based on the information they give us. So our mean sample proportion is just going to be 41% as a proportion, which is either B or D. From there, the question is, what is the standard deviation? And the standard deviation, again, you can see right here, is our sample proportion times 1 minus our sample proportion divided by n. But be really, really careful because this has days in a year, but we only want n to be the days or the amount of our sample size. So the correct answer is B. All right, so your mean sample proportion is the proportion they give you, and the standard deviation follows this formula right here. All right, up next, same idea, they want us to calculate it this time. Okay, so this time the idea is that we want to calculate a sampling distribution of over 500 songs, and we take a sample of 49. All right, now again, one thing to remember is, you can kind of see by the wording of this, if you're thinking ahead, that we sampled less than 10% of our population of interest, so that means what we're about to do with this later on is valid, but anyways, the mean of our sampling distribution is going to be the mean of all the songs, so the mean is just whatever they said the mean was, kind of like the last question. Now this time the standard deviation is, let's look at our formula sheet, the standard deviation is the standard deviation they give us divided by the root of our sample size. So the size that they gave us was 35. That was the standard deviation given. And we're dividing that by the root of our sample size, which is the root of 49. Oops, thinking ahead. Root of 49, which is 7. So we really have 35 over 7, and that's just 5. So the mean is whatever they tell you it is. The standard deviation essentially gets scaled by the root of the sample size somehow. All right, moving on. So let's see here. We have a distribution of success rates in 400 players who attempted at least 20 free throws. And what if we took a random sample of 30 players? Okay, now before we even look at our answer choices, here's how this goes. Actually, we're talking percentages. Give me a minute. Okay, since we're talking percentages, you would expect there to be, let's see here, what is 76%? Oh wait, actually it's not percentage because they said mean. So notice the mean is 76%. So when we sample 30 players, remember 30 is your key of large sample size. So when you sample 30 players, you're going to have a normal distribution for means. 30 or more for means, and then for proportions you need 10 successes or failures. So again, here's what I'm saying here. Because we sample 30 players, we should see a roughly normal distribution about the mean 76. And so this one's about the mean 76. It's approximately normal. There's some outliers going on there. But this one's more normal, about 76. Notice this one isn't even having the center around 76. So that's totally wrong. Because remember, from the last two examples, the mean, or the central point, should be exactly what was in the data. So it should follow along 76 like this, or like this. And this one is just totally wrong. Now, which one looks the most normal? Well, this one looks like it's maybe skewed left because it has that left tail. So I think the correct answer is this one. Because we sampled 30, it should look approximately normal and symmetric about the true mean that they told us, which was 76. All right, kind of same idea here. Let's see here. Okay, so this time we're trying to figure out, did we have an unbiased estimator for the first quartile, which was 70 points? So we took a random sample of 6 tests, we calculated the first quartile, and we repeat this process 50 times. So this is essentially the first quartile of 6 random tests done 50 times. And the question is this unbiased for 70? Now, what does unbiased or biased mean? Unbiased means that it's centered around your value of interest, which it is, and because you can kind of see it's somewhat symmetric. There's some outliers-ish things going on around the ends, but overall it's mostly centered around 70. So to me, that means it's unbiased. because again, it's kind of symmetric, even though there's some unique stuff going on either side. For the most part, it's centered directly around 70, so that means it is unbiased. Okay, up next, let me read this. Okay, so here's what's going on in this question here. We have, again, data about a circuit with a certain thickness, and we know that the thickness should be, so our mean for whatever circuits we sample should be the same as what we expect, which is 200. Now the standard deviation of our circuits should be the given standard deviation divided by the square root of our sample size, which was 16. So this is really 12 divided by 4, which is 3. And now they say, what's the probability that the mean thickness is 3 farther away from the target value? Now this is technically, believe it or not, it seems like an empirical rule question. Because what this means is, what is the odds that you're 3 greater or 3 less than? Well, that's the same as saying, what are the odds that you are 1 standard deviation above or 1 standard deviation below the value? And if you remember the empirical rule, it's sometimes called the 68, 95, 99.7 rule. We know that 68% of the data is inside here, so if 68% is in between -1 and 1, in other words, in between being like 3 units within either side, then we know that, well, what's 100% minus 68%? 32% will be on the outside. Kind of a new question there. Onward. Okay, let me read this real quick. Okay, this is kind of like the last question. So we have our true sample proportion. They say assume the true proportion. So, whoops, sorry, I should write. Yeah, actually, I was right. So assume that the mean of our true sample proportion is just what they told us, which is 15%, and our standard deviation is going to be 0.15 times 1 minus this, which is 0.85. That adds up to 1, divided by how many we sampled. It's still technically in a root, but everything's in a root here. Now this time we want to calculate this with the calculator, so we've got the square root of 0.15 times 0.85 divided by 160. And I'm going to round this to 4 or 5 places, so 0.02823. 0.02823. Now, just general advice, if you ever have to round to like 2 or 3 places, since everything here is rounded to 2 places, it's generally a good idea to go 2 or 3 extra places from what you need, just so that what you do in between doesn't, if you round this to 2 places, you'll probably get an incorrect answer. So always keep your decimal places further than what your final answer needs to be. But anyways, so now we have a mean and a standard deviation, and they say, what are the odds that they find that more than 10% answer yes? Now again, this is a normal distribution question, because essentially we've shown that we have a normal distribution. And so here's what's going to happen. If this is 0.15, and let's just assume that 0.1 is right here, what are the odds that we get something here or greater, all this area underneath? Well, we need to calculate the z-score of getting 0.1, and the z-score of getting 0.1 is 0.1, the actual minus the expected 0.15, so AP, actual minus expected, what you have minus what you thought it would be, the mean, divided by the square, standard deviation. And so let's round this to 2 places. Now the reason I'm rounding this to 2 places is because it's a z-score. We can only figure out what it is to 2 places on the calculator, or on the reference sheet. Okay, so I get negative 1.77. And I should have had this pulled up, but I didn't. Oh wait, never mind, I do right here. A z-score of negative 1.77. 1.77. Make sure, oops. 1.77 is this. Now that's the area to the left and down. I want the area greater than that. So 0.0375, I'm going to do 1 minus 0.0375, and I'll get 0.9625, which essentially rounds to 0.96. There we go. A lot going on there. Again, I needed the area above, and notice the normal distribution always tells you the area below, so I had to do 1 minus. So a lot going on here. Okay, next. Oh, I hate this question. Okay, good news, you're probably not going to see this in the AP exam, but gosh, I could get this wrong. There's a very particular rule here that I don't remember. I always tell my students every year I don't remember. Again, this time it's technically open notes, so maybe this is what you want to write down after we figure out whether we're right or wrong. Okay, here's the idea. They told us that 90%, okay, is the amount of potholes that are completed. So if we sample 75 reported potholes, what's the percent that are completed in 2 weeks? If 90% should be, well, that's 90% of 75. And that's good. That's more than 10. So success is greater than 10, right? It's way more than 10. But failures, what's the other side? If 90% are completed, 10% aren't. Well, what's 10% of 75? 7.5. So the failure is less than 10. And we need both to be greater than 10 if we're approximately normal. If we're less than 10 in some way, we're skewed somehow. And this is what I don't remember. I don't remember which skew it's in. But I'm going to take a guess here. Failure is usually not good. It's like if you're failing, you're less than average, maybe. So I think if your failures are less than 10, you're actually skew left. Now notice this is skew left, this would be skew right. This would be approximately normal. This would be uniform, which is probably never going to show up. So I think it's skew left if your failures are less. If your successes were less, I think it would be skew right. Hey, look, I got that right. And you might want to pause the video right here and maybe write this down in some way that you can quickly see that. Okay, 2 more questions. I've already hit 15 minutes, which means I'm going to have to speed this video up to fit it within 15 minutes. Are we unbiased if the true answer is 32? Okay, this time, notice our data is not centered around 32. It should be symmetric around 32. This is consistently underestimating. It's showing almost every value was less than 32 except for these 2 random tests. So this is definitely biased because it's always underestimating the population range. Again, pause it, read the question, but the idea is all the values are less than what you were expected to find. You're supposed to see things centered around 32. Instead, almost everything is less than 32, so we're clearly biasing somehow. Okay, last question, and then again, it's kind of a normal CDF question, so I'm going to go a little quicker this time. So first we have the claim, which is what we're going to take to be our mean, that it's 0.45, and we're about to do a random sample of 200, so that means our standard deviation is going to be 0.45 times 1 minus that, which ends up being 0.55. They have to add 1. All over the square root of your sample size, which is 200 in this case. Now 200 isn't the root, I didn't write that nicely, but just know that. So 0.45 times 0.55 divided by 200, and I'm going to round that to 5 places, just since it's my intermediate work. 0.0357517, no, 518 if I'm rounding to 5 places. Okay, so I've rounded that to 5 places, and now the question is, what are the odds that we fall in between 40 and 50? Now, technically, I guess I'm going to do this the long way around. Yeah, okay. Let me quickly calculate the z-score. I might skip the video here, and we need to calculate 2 z-scores. The z-score of 40 and we need the z-score of 0.5, 50%. Divided by the same standard deviation. Okay, now here's what I'm going to say. After you find both of these z-scores, find their associated area to the left as is, and then just subtract them. But here's what I'm going to do. I'm going to use my calculator. Hopefully you have a graphing calculator. I know not everyone does, but again, what I just said, find the z-score for this and calculate the area to the left. Calculate the z-score for this, find the area to the left. And what you would then have done is essentially you would have calculated the area of finding 0.4. Here's 0.45 in the middle, what you expected. Here's 0.5. And since you found this area to the left and all of this area to the left, when you subtract them, you're canceling this out and you're getting the area that you wanted in the middle, in between. So when you subtract the total area from 5 all the way down to 0.4 all the way down, you're getting the area in between, which is what you want. So long story short, let's do that in the calculator. Here's how I'm going to do that. We have normal CDF, and I want my lower to be 0.4, my upper to be 0.5. My mean was 0.45. My standard deviation was 0.03518. And it turns out it's 0.84 something something, and there we go. Okay, so good luck through this assignment. Again, use your z-tables carefully, and this is a key unit to getting through the second half of what I call the second half of this course, so make sure all this makes sense.